Okay, I will get started and just go through some of the housekeeping things at the beginning. Thanks everybody for joining today's TRANS-IPIC Research Highlights webinar for March. We got two great talks today that will be coming up in just a moment. Before I go into those, I just wanted to do a quick couple housekeeping notes about the upcoming workshop. So next month on the 14th is our yearly workshop, the Transportation Infrastructure Precast Workshop, or TIP. TIP 2026. It's going to be happening on the 14th of April. And just a quick note for some of the faculty that are online, the manuscript submissions for the proceedings that we will publish should be submitted to us by the 27th. And then we're happy to be including this year a student best poster award. So we'll be doing that throughout the day. And then we're actually working on adding a precast panel, which is pretty exciting. So we may have some slight agenda updates coming for everybody pretty soon. So without further ado, I'll get rolling here so we can keep on track with our timing. As I said, we have a couple of great speakers. The first is a team from Purdue. So we have Dr. Jiansong on the line. He's an associate professor of construction management technology at Purdue University. He's the founder and director of the Automation and Intelligent Construction, or AutoIC lab, which develops scientific theories, methods, and advanced technologies to support construction, engineering, and management, construction automation, and sustainable and resilient built environment. He's also the founder and director of the Digital Twin and Robotic Automation Center for Knowledge Sharing, Entrepreneurship, and Research, DigiTracker at Purdue. And this is kind of a neat, he's recognized as the father of invariant signatures in AEC, which is a very cool title. Anyway, please take it away.
Thank you so much, Chris. So good afternoon, everyone. It's great to see Professor Andrews and colleagues, everyone in the meeting here. So today, I'm going to talk about how we, through the support of the TRANS-IPIC project, we are trying to implement the invariant signatures of AEC objects in civil infrastructure projects. So I'm going to present on behalf of our team, including Meta Soy, Ziri Hong, Fan Yang, our students, myself, and also Professor Hubo Cai. So a little bit of background regarding the topic that we're going to cover today. So building information model or building information modeling, BIM in short, it has been a very important research area, research topic in our architecture, engineering, and construction domain, AEC domain. And there are so many different software platforms by different software vendors. And when we try to move the data or the model from one platform to another, there can be challenges in terms of the difficulty in moving the data in the first place. But even if the data can be moved, there can also be inconsistency or missing information. In order to address this problem, so a lot of the converters, can be developed between each pair of those software platforms, right? So in that case, let's say if we have n number of software platforms in the market, then technically, we need to create, select CN2 number of converters, right? Which is a quadratic relationship with regard to the number of software platforms existing. So with that being said, the Building Smart organization, they have published the industry foundation classes, IFC standard, which also has been already adopted as an ISO standard for our AEC industry in general. So the idea is that all the different software platforms, if they can be importing from and exporting into the IFC data format, then we don't have to have n squared, right, to that level of number of converters needed. Instead, we will have a linear relationship. Basically, if there are n number of software systems, then we only need n converters to and from the IFC model. So with that being said, obviously, the IFC data standard has greatly facilitated what we call it BIM interoperability, again, which means the data transfer between the different software platforms. But still, even if for the most stable and mature, well-developed part of the IFC model, the geometric representations, if we import the same IFC data into different software platforms as what you can see on the screen, we can still get very different results. So with that being said, about a decade ago, me and my colleagues back then at Western Michigan University, that was my first job, with Dr. Xiaoyun Shao and Pina Rieger, we came up with this hypothesis that if we could define invariant signatures of an AEC object, collectively defined by the Cartesian points-based geometric, relative location and orientation, and the material mechanical properties, these are expected to enable the seamless and universal interoperability of BIM, beyond what IFC standard already supports. So our initial contacts were said to be the interoperability between architectural design and structural analysis, as well as between the architectural design and construction cost estimation. So back then it was NS National Science Foundation project that we worked on. So this is another look at this invariant signatures idea. At the top of the screen, we can see many signatures by individuals, right? So I guess we all sign a lot of paperwork daily, and we all have our very unique signatures. So what do signatures do? They help uniquely identify individual in that sense. So then the idea is that could we also have signatures for the objects in the AC domain in general, right? So then in that case, what should be the components of that signature? And obviously, the most mature and stable part should be the geometric representation. But in addition, we may also have locational information. And this is not just the absolute location. It can also be the relative location with regard to another object. And also, we could have the mechanical and material properties, which also are supposed to be stable. So with that being said, back in 2021, we defined the invariant signatures of an AEC object to be a set of intrinsic properties of the object that distinguish from others and that do not change with data schema, software implementation, modeling decisions, and/or language cultural context. So basically, these are the dimensions that still were creating challenges for universal seamless BIM interoperability, even if all the software systems adopted the IFC standard, right? So the invariant signature in that regard is set out to address these challenges. So the invariant signatures should uniquely describe the object and provide all the information needed for various analysis. And this table 1 here shows an example invariant geometric signatures of AEC objects in a rectangular parallelepiped shape, which is probably one of the most common shape, in terms of AEC projects, AEC objects. As you can see, basically we look into the detailed composition of the geometry and we count, how many components there are, how many faces, what is cross-sectional profile, what are the dimensional ratios, how many lines and curves, what is the boundary line connection angle, etc. So the initial set of features, we included 9 of them. With that being said, this is not it's not a fixed list. It can be extended based on the scenario and application. So in addition to the rectangular parallelepiped shape, we also developed the geometric signatures for the common shapes such as the I shape, which is pretty common in I-beams and I-columns. And also we looked into the cylinder shape and ring shape. We defined geometric signatures for the different shapes to get this started. And we also came up with a 5-step method for applying the invariant signatures to solving a practical problem. And when we say practical problem, we are looking at specific interoperability scenarios. For example, we may want to have interoperability between architectural model and the structural model. So that is one example scenario. So the 5-step method that we have developed started with the problem definition, right, which identify and define the specific scenario for interoperability. And then the second step will be about collecting data. And if the data cannot be readily collected, then they may need to be created from scratch. After which the data will be pre-processed into formats that can be actually apply the invariant signature extraction so that we can extract those invariant signature features and their values. And then we keep evolving the invariant signature data. And we try to apply that to compose algorithm that will be able to help us with automatically transfer the data between the two different scenarios. And based on the algorithm test, we will iteratively, evaluate and refine the algorithm until a predefined threshold has been met. So after that, we'll get into a final evaluation to see how good that algorithm can perform to deal with that task. So with that being said, here we can look at one example scenario. Let's say between the architectural design and the structural analysis interoperability, we develop invariant signatures in terms of the geometric properties and material properties. And then those properties are used to compose or compile the conversion algorithm that will be able to take the architectural model and automatically generate a structural analysis model. And in the figure 7 on the bottom right, you can see this is one result from the experiment that if we put together side by side the gold standard on this side, the gold standard developed by the subject matter experts, and the automatically generated results from our algorithm, they can, they can be pretty consistent. In the final evaluation, the converter that we created based on the invariant signatures were able to achieve 98% precision. So with that being said, we also tested the invariant signatures idea in multiple different interoperability scenarios, such as between the architectural design and the building energy modeling, between architectural design and building energy simulation, between the architectural design and building code compliance checking automation, as well as between the architectural design and automated cost estimation. In addition, because of the workforce shortage that the whole industry is facing and the uprising interest in terms of construction automation with robotics, we also looked into how we may actually convert the initial design model from the FC format together with some robotic system information to automatically generate a simulation that can actually be used to evaluate whether or not that piece of robotic equipment can be used to help with the construction operations. So as the result of this workflow, this can generate a simulation like the one you see on the screen here. So basically here we are evaluating how a robotic arm can be used to put together a timber frame. And at the end of the simulation and evaluation, the system will automatically generate a report that tells us, okay, in this application scenario, what are the potential issues and the problems, right? Like in this case, you can see there might be the auto reach scenario, which means the timber component is beyond the reach of the robotic arm. There also might be potential collision, which means if the path planning of the robot is not very well developed, then the robot may collide with the component itself or with the tool table. So with that being said, we have achieved a lot of successes in implementing the invariant signatures from the building construction sector. So we also looked at how the invariant signatures may help with the civil infrastructure projects. So then in collaboration with the Indiana Department of Transportation, we investigated how the invariant signatures can help us, facilitate the quality assurance of the drainage network. So what you see on the screen on the top left are some different types of drainage nodes, inlets, particularly On the top right in this table, you can see the example geometric signatures that were derived based on the data collected in collaboration with the Indiana Department of Transportation. And then at the bottom, you can see the application of the invariant geometric signatures to automatically identify or classify the different types of drainage inlet nodes. So with the support from the TRANS-IPIC Center, in collaboration with my colleagues, Professor Hubo Cai, Joseph Dunstan Philip, and Professor Dulcie Abraham, with our students, Zray, Meta, and Aria, we are also trying to implement the invariant signatures in two contexts. The first one is the life cycle quality checking, quality assurance for the prefabrication scenario of the bridge or MSE walls, of bridge panels or MSE walls. So this was a project led by Professor Hubo Cai. And we also look at the construction scenario where we start from the design of a bridge and as well as the selection of crane, including its load capacity, range capabilities, those parameters. And we try to automatically extract information from the bridge design using the invariant signatures for automatically identifying the different components. And then we try to automatically generate operational plan for the mobile crane to install, or in other words, construct the bridge, right, using the prefabricated bridge decks. So the bigger vision that we have is actually with this type of let's say logic-based algorithm that can help us automatically plan for the operation. We can in turn leverage that plan to help us monitor the actual operation on site when the construction is actually going on, right? We can leverage different sensing capabilities and then compare the monitored progress with our original plan. And whenever there is a deviation, right, so the system can decide if that deviation is serious or not. And if it's a serious deviation that requires attention, then that can be sent back to the operator or the project manager, whoever is controlling or managing the job site, to take countermeasures, right, or mitigation measures. So that is the vision we have in terms of the prefabricated bridge construction context. And this will be the focus of today's presentation. So with that being said, we started by data curation. We developed the bridge design models because we didn't really find readily available models that can be directly used for this purpose. So develop our own bridge utilizing the different beam authoring platforms such as those from Autodesk and Bentley. And after which we exported those models into the industry foundation classes IFC format, utilizing the different versions of the IFC standard. So with that being said, although IFC is an ISO standard and is widely used now in the industry, but it has been continuously developed. So they may publish a newer version, right? Every let's say every now and then. So we have been focusing on IFC 2x3, which was one of the most stable version of the IFC standard, and IFC 4, which was the version that started to incorporate explicit representation of bridge products, as well as IFC 4x3, which is a slightly more advanced version compared to the previous two. So the figure on the left shows the workflow in terms of leveraging invariant signatures to extract the data from the IFC models. Most importantly, the slabs themselves, as well as the bridge body, And the most important parameters that we would like to extract is really the geometry for the different bridge deck that can help us automatically identify is it a bridge deck in the first place, right? As well as the physical properties such as the mass that can be calculated based on the geometry and the density, etc. So we use the properties from the geometric invariant signatures to automatically identify the different component types, as mentioned earlier. So the benefit of this workflow based on IFC and invariant signatures is that it can actually work across different beam authoring platforms. So it's not limited to any proprietary beam authoring tools. And also it supports different IFC versions, such as IFC 4, IFC 4x3, even the older IFC 2x3. So we successfully extracted from the bridge models, the slab ID, the locational coordinates, their dimensions, the mass properties, and the bounding box vertices. And once we have those information, we will feed those information automatically. Again, this is part of the workflow. So those information will be fed to the two-stage heuristic planning part of the system. The first stage of the two-stage, we call it capacity-based filtering. So this is basically emulating the traditional Korean capacity selection process, right? So basically, if you're familiar, the conventional process, we look at a chart and we look at the capacity of the crane, the range, the load capacity, as well as the need of the project itself to determine what are some of the potential feasible, combinations of the crane parameters. So in this chart, what you see specifically, we are highlighting the valid options in the scenario for load heavier than 10 tons. And the second stage, we call it geometric constraint filtering, which includes three major geometric constraints to ensure safe lifting of the mobile crane on the job site. So the first is the boom load collision prevention. So this is where we would like to have a plan that can prevent any collision between the boom of the crane and the bridge deck itself, right? So you can see we have the equations 1 through 3 that we look at the positions and the height and the turnaround radius of the load itself and set up those constraints so that, in this scenario, the bridge deck will not collide with the boom of the crane. And also, we also want to prevent the collision between the boom of the crane and the bridge itself. So the second geometric constraint, we call it the rope length constraint. So this is a little further derivation from the previous constraints. If we use R to represent the length of the rope, then obviously we would like that, first of all, the minimum length of the rope need to be, long enough so that when the bridge deck is lifted, it will not collide with the boom. That's on one hand, and then on the other hand, when the load is being mobilized to the placement location, we also would like that the minimum length of the rope to not be too long, right? Because if it's too long, then you may not have enough gap here to allow the bridge deck to be hoisted taller and higher than the bridge structure itself. And the third constraint, we call it boom bridge collision avoidance. This is in terms of the lifting angle, basically. If you focus on the C figure, figure C of this figure at the bottom, so basically we can have the two angles, and alpha 1 and alpha 2, right? So we use alpha 2 to help us determine the angle, which is like the edge boundary that will determine if the bridge, if the boom may have contact with the edge of the bridge, right? And obviously, we would like the alpha 1 to be greater than alpha 2. So next, I will talk about the simulation for the constructability analysis. So essentially, we took the information that came from the IFC model that we automatically extracted, leveraging the invariant signatures. And then this information automatically fed into a game engine-based simulation environment and creates this virtual scene. We're using Unity 3D particularly, and also to help with the planning of the operation of the crane, we leverage what's called the behavior tree, BT, and this is a clearer look at the behavior tree. So on the top, we have a node that defines the sequence of the operation in installing the different bridge deck panels, again, the precast panels. And at the bottom, you can see we have the corresponding nodes for installing the different bridge panels. And so if you think about the installation of a particular bridge deck, again, precasted bridge deck, this can be a pretty repetitive operation. Although for each and every bridge deck, the parameter might be slightly different in terms of its final location, etc. But the overall, sequence of operations, let's say starting from the hooking up with a rope and then lifting it up and then transition it horizontally to move it into the installation location and then lower the bridge deck into place, right? So that process is pretty similar across the different bridge decks. So we leverage that what's it called repeater node, which means this process can be repeated for the different bridge decks. And this slide shows the high-level logic in the system. So basically, once the crane selection has been finished and we have a site layout already set up, we can then apply our heuristic, logic-based pre-execution planning algorithms to automatically analyze what are some of the feasible combinations of the, parameters of the crane as well as for the bridge decks. So if a feasible plan is found, then we can move to the next step of executing the plan generated by the algorithm with the visual assessment, side by side to help us, monitor it as well, to help identify any issues during the execution of the plan. And if there is no problem, no issues identified, then that plan can be finalized. So with that being said, if there were any issues identified either in the pre-execution planning stage or in the execution simulation stage, if any issues such as failures, collisions, excessive sway, crane tipping, inefficiency, etc., those could be provided as feedback to the user so that the user can decide, if they want to refine the plan, if they want to change the configuration, or what is the mitigation that what they want to execute. So once the system has been developed, we put it into test with 10 test cases. So this figure here shows some screenshots during the test. For example, we have 10 bridge panels. Panel number 1 and 2, during the evaluation, they were found to have issues. And then for the rest, panels 3 to 10, they were found no issues. So the issues of the first two panels were, for the panel 1, it was the auto reach scenario. So basically the placement location is beyond the crane working radius, again, based on the selected crane and the job site configuration. And then the issue for the panel 2 was the identification of a potential load bridge collision. And for the rest 8 panels, they were found no issues, and therefore they were successfully executed and the plan finalized for these 8 panels. So with that being said, through the test cases, we found that the system feedback was effective for operator to adjust the plan. And in our system, the parameter calculation are fully automated, so there's no manual calculation needed and at any stage. Uh, Also, in the system, we provide the visual constructability verification because the simulation can be monitored by user in real time. And also in the simulation, the collision can also be detected in real time if there is any ever collision risk. And in the end, the simulation can automatically generate the complete installation sequence. So with that being said, we would like to highlight the contributions of this project. So first of all, we demonstrated that the invariant signatures can be also applied in this particular scenario of precast bridge installation. That the robust FC extraction can be supported across the different platforms, the different beam authoring tools and versions of the FC model, FC standards. And the system can provide automated feasibility assessment of crane operations to help with the planning of the precast bridge construction. And also the system allow interactive constructability analysis because we have this simulation interface that the user can monitor in real time. So with that, the operators can test multiple scenarios before the on-site work. So this shows the practical value of this project. And the system can provide systematic evaluation of the crane positioning and selection, and therefore the system can help reduce the operational risks, and as a result, it help improve the safety of the operation itself. So with that being said, we also would like to acknowledge the limitations of the current shape of the system because it was built based on this Unity game engine. So it does require some familiarity with the simulation engine to be able to use the system. But we are looking to improve that so that user in the future will not need any familiarity with the simulation engine. Also, the system currently is based on some assumptions, with the most important one being we assume there is a clear space, which means in the surrounding environment is completely clean and clear. There are not tall structures surrounding the job site. There are also no other operations happening that may interfere with the precast bridge installation. So in the future work, we also would like to see so first of all, the user interface obviously can be enhanced. Currently, it's a pretty preliminary GUI that we have, but we also would like to connect all the pieces into a fully automated pipeline that will further reduce any needed attention and efforts from the user. We would like to add more constraints in addition to the three that we have presented in detail. Last but not least, we also would like to connect this system to the real physical world. So with that being said, here we are showing some of the initial efforts towards that vision. So these two figures here shows smart crane concept that we have developed, at our mouse construction lab at Purdue University. So basically, we try to convert this traditional crane into a smart one, right, by hooking it up with the digital control, algorithm control. And we also are developing sensing capabilities that can help us automatically monitor the operational status of the crane. So this figure shows some initial efforts from these undergrad students, Anaya and Pranav, who have looked into how to automatically sense the crane status with LiDAR equipment, and also with segmentation algorithms and other analysis algorithms to automatically detect the orientation of the crane boom as well as the position of the hook as well. So on the
I
top
think
right,
I think we're a
we're
little
on
bit over
time.
time. Yeah,
Okay.
do you could we maybe get your last
Yeah,
comments, and then we'll
I'll
probably have
skip
to.
to the last. Right. So
Okay,
again, this is this vision that we have talked at the beginning. So in conclusion, by implementing the invariant signatures concept with the extraction process, we bridge the critical beam to simulation gap, and the pipeline enables systematic pre-planning evaluation in the simulation environment. The pre-planning simulation could reduce the onset risk and improve safety, and this we validated it across multiple platforms and IFC versions. In the end, we would like to acknowledge the support. The background material was supported by INDOT and NSF, and we would like to thank the TRANS-IPIC Center to provide the opportunity for us to investigate this under the project PU 24 EP-01. Thank you so much.
great. Thanks so much. Maybe we could do one quick question if anybody has one. If you want to type it into the Q&A button at the bottom, or if you raise your hand, I can allow you to unmute. If anybody has a question, thanks so much for that presentation.
Thank you, Chris.
Yeah, just give it a second. Not seeing any raised hands. Q&A. Okay, I guess I think you're great. So we'll move on to the next one. Thanks so much, Dr. Zhang. Now we'll move into the next presentation of the webinar. Really excited to have the team from Louisiana State talking today. So we have Dr. Hai Lin. Dr. Lin is an associate professor in the Department of Civil and Environmental Engineering at Louisiana State University. He earned his PhD in Civil and Environmental Engineering from Lehigh University in 2016. Dr. Lin's research focuses on bio-mediated and bio-inspired geotechnics and soil structure interaction. His work has been supported by the National Science Foundation, Department of Transportation, and Louisiana Board of Regents, and the Louisiana Transportation Research Center, LTRC. He received several awards, including NSF Career Award and the Ralph E. Howe Junior Faculty Enhancement Award. So really excited to hear what you have to talk about today, Dr. Lin.
Yeah, thanks, Chris, for the nice introduction. My slides looks good. Okay, so
Yep.
today I will be talking about fungal self-healing cementitious material, which is a preliminary study. I like to acknowledge my graduate student Noah Bao. He actually did majority work for this project. I also want to thank my co-PI, Dr. Yin-Fang Su, and then the funding support from TRANS-IPIC. So this is my presentation outline. So first I'll give a brief introduction, and then I'm gonna dive into the fundamental processes that can contribute to uh, healing in the cementitious material, which is this process. It's called microbial induced calcite precipitation. And then we'll talk about research goals, motivation, and then we're going to dive into fungi. What is the fungal mycelium, and why we recently we look into this fungal mycelium-based composites, and then I'm going to talk about the mechanism that may contribute to healing in the cementitious material. And then I'm going to share a couple of research tasks results, followed by conclusion and future research. So we all know that concrete can develop cracks during the curing and service. Um, and these cracks can reduce load-bearing capacity, affect service life because a lot of substance, right, they can penetrate through the cracks into the reinforcement, leading to concrete spalling. So that's why nowadays we have a lot of self-healing technologies. One option is basically we can encapsulate chemicals to the concrete or cementitious materials. But sometimes these chemicals they are not compatible with the concrete composition in terms of mechanical and thermal properties. So in some cases, actually, this incompatibility can cause some issues. And then another option is bio-based self-healing. Rely on this microbial metabolic activity, which is called microbial-induced calcite precipitation, MSCP. So this process, the reason we want to use this for heating cracks is basically they have so by using this process, the process can generate CaCO3, which is a calcite, and this calcite basically has excellent crack filling capability, strong bonding between the calcite and um, the concrete material, and then they show high compatibility with the concrete composition and better thermal properties. And apparently, it's more sustainable because the bacteria or fungi they can self-grow. So here is an example of the crack healing uh, by a bacteria strain. Um, so so here I just want to briefly talk about what is this process, the fundamental process that contribute to crack healing. This is called microbially induced calcite precipitation, MSCP. So this figure shows the schematic reaction. So if you look at this figure, and we can see we have one bacterial cell here, right? So this bacteria is called Sporosacina pasteurizii. So this bacteria actually stick to a particle surface. So this particle could be a gravel, sand, or even cement particles. So this bacteria, they have some enzyme that they can hydrolyze urea into ammonia and carbon dioxide. And then ammonia, carbon dioxide, they go into the surrounding solution. They're gonna form ammonium and bicarbonate. And if we have calcium in the solution, we're gonna have this reaction. So eventually we're gonna have calcium carbonate precipitate. And then these calcium carbonate precipitate, they're gonna nucleate around the bacterial cell because of the charge. Right? So eventually more and more calcium carbonate precipitate, and then they're gonna basically embed, they're gonna precipitate by surrounding this bacterial cell, and then eventually the bacterial cell will be embedded or buried inside this calcium carbonate mineral. And then the crack healing is basically due to this mineral precipitation, which is calcite. So if you look into the literature, there are already several studies. They evaluate, like, see if this MSCP process can heal concrete cracks, right? And then you see here from this study, they observe very effective healing, crack healing by using this MSCP process. But there are some limitations of MSCP. So first thing is the byproduct, which is ammonium. It may be harmful for the surrounding environment. And then when the crack width is larger, sometimes it's hard for bacteria to heal those larger cracks. And then the third limitation could be this could be just one-time treatment because uh, when we have more and more calcium carbonate precipitate, the bacterial cells they're gonna be buried or embedded inside the calcium carbonate mineral, right? So in this way they stay inside the mineral, and then there's no way they can keep themselves alive and then continue induce calcium carbonate precipitation. So this could be just one-time treatment, and then there's no probably it's gonna be hard for them to heal future cracks. So here for our project, we like to explore fungi because there's a limited studies on using fungi to heal concrete. And then we hope the fungi can somehow improve some of these limitations. So the research goal of our project is basically to explore fungi, explore fungal metabolic activity based on this fungal induced mineral precipitation and see if they can heal cracks in the cement mortars. Right? So the motivations are basically, if you look at these here, two different microorganisms. One is the typical bacteria E. coli, and the other one is of fungi or fungal mycelium. And if you look at the shape difference, the bacteria usually they are rough shape, but for the fungi, they usually grow in the form of fungal mycelium, which basically is a cluster of mycelium fibers. And if you compare the surface area, you can see the fungi have enormous surface to volume ratio. So that means with this type of morphology, we're gonna see more uniform mineral precipitation for crack filling. And then this type of morphology may be able to enable fungi to survive, to better survive in the concrete environment than the bacteria. And then a lot of fungi, they actually have very high, they have higher growth rate than bacteria. So that means in the same amount of time, the fungi, they actually can grow into a bigger area, which can help quickly heal the wider cracks. And then if they were broken, they can heal themselves. So there's a potential that they can stay in the cementitious material longer, even with the nutrient poor and alkaline environments. And also another beauty of fungi is they actually can turn the material surface to hydrophobic conditions. So that means the water will be hard to go into the cracks because the surface is going to be hydrophobic, right? So this will reduce the water permeability of the material. And then in the literature, there are already several studies. They look at fungal self-healing process, but they didn't really look into or they didn't really investigate the fungal self-healing for cracks. What they did is they just grow fungi on the surface of a concrete or cementitious mortar to evaluate the livability of fungi. So they never did a real crack healing using fungi, which was explored in our project. Right. So before I dive into the research task and results, so I do want to talk a little bit more about what is a fungal mycelium and why we care about this fungal mycelium. So fungal mycelium is actually the root structure of the mushroom. Right? So for fungi, some fungi they can form mushrooms, some fungi they can form molds, but fungal mycelium is basically the root structure of the mushroom. Right? So here shows accelerate movie showing how fungal mycelium they grow uh, away from the center. Right? So for fungi, they actually they take 25% of total biomass on Earth. Actually, the fungi they are actually the largest, the oldest organism on Earth. There are many species, just small amount of species. They are pathogenic and parasitic. They have rapid growth rates. Some fungi they can even grow 20 millimeter per day by just extending the fungal mycelium. They can grow in nutrient deficient condition. If they were damaged, they can heal by themselves. And then there's a low carbon and low cost because they basically, if we just give them a little bit nutrient, they can self-grow. Right. So nowadays, just I want to expand this a little bit more. So a lot of people they are looking into developing a fungal mycelial biocomposites. Right. By developing this composites, it's basically easy. What we need is just some agricultural waste or wood chips, and then we drop the fungi into this material, and then with time, you will see a fully connected biocomposite with agricultural waste fibers and also fungal mycelium. So people are actually developing uh, this fungal mycelial-based composite as an insulation material to replace conventional insulation material. We can develop packaging material using fungal mycelium and agricultural waste, furniture, some fashion clothes, purse. Uh, and then people are actually even looking into using this composite material as a construction material for buildings. So now let's come back to the another mechanism that fungi can do is some fungi can even induce mineral precipitation. So this is basically a motivation why we want to use the fungi to heal cracks in the cementitious mortar because they can induce mineral precipitation. And then in the literature, there are typical three type of metabolic processes of fungi that they can induce mineral precipitation. The first one is acid oxidation. Second one is the urea mineralization, and then nitrate assimilation. We did one preliminary test using this urolithic fungi to induce urea mineralization. So this is an SEM image that we prepared. So if you look at this photo, you can see these circles, right? These are sand particles. And then the stuff in the pore space, those are fungal mycelia, and then later uh, the mineral precipitate, which is a calcium carbonate precipitate surrounding the fungal mycelium. So this is basically the preliminary study we did. And then when we look into these three metabolic activities, we prefer using this urolithic fungal strain to explore concrete self-healing. So for this project, we're going to use urolithic fungal strains. And then by reading through the literature, and we noticed there are three fungal strains, Trichoderma raceae, Neurospora crassa, and Aspergillus niger. These three fungal strains, they were found that they can precipitate minerals through urea mineralization. Uh, so for our research, the first thing we want to do is look into these three fungal strains and then see if they can really precipitate minerals. And then if they can precipitate minerals, what type of mineral they can precipitate. So what we did here is we basically grow these three fungal strains. So first we grow these three fungal strains in the growth media in the glass flask, and then we grow them for 10 days so that they can grow into larger population. And then we add into the flask with another medium, which is called cementation medium. Here's the chemicals added into the medium, and then this media will help fungi to precipitate minerals. And then after that, we're gonna filter the solution. So we're gonna remove the liquid, and then we're gonna collect the retained material on the filter for X-ray diffraction analysis. Right, so let's take a look at the XRD results. So here we just want to look at, what type of mineral they can precipitate. So this first XRD figure, this is the mineral we detect from the Neurospora crassa, and then it's basically calcite, which is a calcium carbonate, right? And then the second figure is the mineral detected from the Aspergillus niger. So they actually precipitate this calcium oxalate. And then the third fungal strain, there's no mineral detected. So we basically remove this fungal strain because they basically didn't precipitate any mineral. So from this task, right? So we confirm these two fungal strains they can precipitate minerals, and then there's a potential they can heal cracks in the cementitious material. So next, we're gonna focus on using these two fungal strain to heal the crack mortars, right? So for this self-healing mortar test, we prepare several samples. We have the first sample control sample. So basically we add cement, sand, water, and then some chemicals, but no microorganisms. So this is basically our control. And then the second sample, we have the sample by adding this bacteria as pasteurized, right? And then everything else will be the same as the control, right? And then we have SPF, which is the bacteria plus fiber, and then the rest two are basically the two fungal strain with fiber, right? Here, the reason we want to add fiber is based on the literature. The fiber is going to be beneficial protecting the bacteria and the fungal strains because bacteria fungal strain they can stay in the fiber and then so the fiber can basically protect them from the concrete environment. So for these samples, we actually prepare three sets of samples. The first set of samples will be used to measure the 28-day curing strength, right? So these are the sample numbers. And then the second set of samples, we crack those samples after 28-day heating, 28-day curing, and then we let them go through the heating process. And then the third set of samples, we basically crack them, we let them go through the same time as these heating samples, but those samples are unhealed. Right? So basically, we prepare those samples in this size mortar cylinders. This is the cement sand fluid ratio. We first did the dry mix, and then we add fluid into the mix, and later we add fiber microbial cementation suspensions. And then we let the samples cure for 28 days. Here's the photos that we prepare these samples and let them cure for 28 days. And then we crack them by doing splitting tensile loading. Right, so here are the samples, like how we crack the samples. And then we let the samples go through these 112 days of heating by doing this wet dry cycles. So let's take a look at results. So this is the 28-day cured compressive strength of the motor samples. So these are basically the compressive strength just after 28-day curing. So this is the control. Here, then this is basically the average compressive strength. Um, Here shows the sample numbers. And then what you see here is these two are the bacteria samples, one without fiber, one with fiber. Right? So you can see here the bacteria samples, they are a little bit lower than the control sample, right? But the fungal samples, the ANF, the NCF, they show much higher compressive strength than the control and also the bacterial samples. So here, the higher strength uh, of the fungal samples needs further investigation about why we see higher strength. And then, so after this 28-day cured compressive strength, we start cracking the samples. And then once we finish cracking the samples by doing those split tension, what we did is basically want to monitor the healing using shear wave velocity measurements. So what we did is we use band elements, and then we basically put band elements on the opposite side of the cylindrical sample, and then we want to measure that shear wave velocity. Right. So what we did is basically by using these band elements and then using the equipment, we can measure the shear wave travel time. And then we know the diameter of the cylinder, right? So diameter of the cylinder divided by the travel time, we get a shear wave velocity. And then we basically regularly measure shear wave velocity during the heating process. Right. So here are the results of the shear wave velocity data during heating. What you see here is each figure represents one sample type, right? At the beginning, so you will see at the beginning we have a sudden drop of the shear wave velocity. This is basically due to cracking. So before cracking, we have shear wave velocity around 900 meter per second, and after cracking, they drop to about 300, right? And then after this drop, we're gonna monitor shear velocity measurement during curing, right? And then if you look at the numbers, so here we compare the final average shear wave velocity, compare this average to the average of the cracking shear wave velocity. And you will see for the control sample, so here there's no microorganisms. The shear velocity increased by 20%. With bacteria, the increase is about 100%. AN fungi increased by 100%, and NC fungi increased by about 67%. So the increase of shear wave velocity meaning there's a healing ongoing in the sample, right? And then the best results happen in this AN fungi bacterial sample, followed by this NC fungi and also the control sample, right? We also took photos on the sample cracks during heating. So these are the examples. So this is the sample. We have fungi in the sample. So with time, you can see the cracks were healed. And this is the sample with NC fungi. And you can see the cracks were also partially healed. And then after heating, we did another compressive strength test. So if you look at this figure, the darker column is basically the unhealed samples, and then the lighter column is basically the healed samples. So here we have the control sample, right? The healed sample increased, the compressive strength increased by 51%. SP bacteria increased by 23%, SPF 80%, AN fiber in heating increased strength by 76%, and then NC fiber increased strength by 63%. Right. So if you look at these absolute strengths, you can see the bacterial samples are still lower than the control, right? But the fungal samples, they are much higher than the bacterial samples and the control. And then if you look at the percentage, the best healing happened in this SPF, and also the AN fiber followed by the NC fungi control and SP. Right? So from this figure, we can see the bacteria and fungi, they show very good healing effect compared to the control. Right? So here are the conclusions. So from the XRD analysis, we found out that these two fungi, they can precipitate minerals. One is calcite, the other one is calcium oxalate. And then by doing shear wave velocity monitoring, we see healing happen because we see shear wave velocity increase. And then when we look at the healed compressive strands and unhealed compressive strands, we see the best healing happen in this bacterial fiber, the fungi, the AN fungi with fiber, followed by the NC fungi with fiber control, and also the bacteria without fiber. So the compressive strands give us indication that using bacteria and fungi is feasible to heal cracks in the cement mortar. And then for the future work, right? So we see some macro scale, right? The strength improvement, the photos, the shear wave velocity measurements. So for the future work, we like to do more micro scale characterization using XRD and TGA to figure out what mineral precipitate and how this mineral microbial activity interact with the cement hydration. And then wanna uh, look more into the crack condition, crack width, closure ratio, and look into crack healing efficiency through digital imaging. With that, that's my presentation, and I'd love to hear some questions.
Thanks so much. That was fascinating, especially to see the increased strength that can be gained. If anybody online has questions, you can type it into the Q&A, or if you raise your hand, I can unmute you. If somebody would like to ask any questions for Dr. Lin.
Yeah.
I'm not seeing any yet, but I'll give it a second longer just in
Okay.
case. Yeah, I guess. Okay, I don't see any questions coming in, so I think that's it.
Okay. Thank you.
Yeah, it was great. Thanks so much to both of our speakers, Dr. Zhang, Dr. Lin. It was great presentations today, and then we'll have the recording from this will be up in a few days for anybody who'd like to view it later. And then if you haven't, please check out the workshop coming up next month on our website. And we got some great speakers. Should be a great event. Anybody who's interested, please join us. Thanks so much for attending.
Thank you, Chris. Thank you, everyone.
Thank you.
Thanks. Bye, everybody.